Welcome back, students. We are on to our next unit. We're going to be talking about stoichiometrics and how we use stoichiometrics with chemical reactions. We're going to be talking about some very important terms like theoretical yield, limiting reagent, and percent yield, and how to calculate those. So some things we're going to go over in this particular unit is we're going to do stoichiometrics with chemical reactions. We're going to convert from grams of a reactant to moles of a product or grams of a product. We're going to convert from grams to molecules, atoms, or formula units with a chemical reaction. And we're going to talk about the theoretical yield, limiting reagent, and percent yield, and how you can come up with calculating those. The last thing we're going to discuss is we're just going to briefly dive into a little bit about chemical reactions and heats of chemical reactions. We're just going to touch on this just a bit. Okay, so let's start off with what is a chemical reaction? And we've learned these in the past. A chemical reaction is simply when we have a reactant, one or more reactants, that go to a product. So the reactants change to a product. Now, in our case, those reactants going to products, usually we see an arrow that is some sort of process. But what we know is that what's on the left-hand side of the equation equals what's on the right-hand side of the equation. Previously, we had talked about balancing these particular chemical reactions. So when I'm balancing a chemical reaction, I put coefficients out in front of my reagents and or products. So in other words, I get a to the a plus b to the b, c to the c, plus d to the d. Whereas in the lowercase letters represent my coefficients. Okay, these particular coefficients are the number of moles that I have for that particular chemical reaction. So, if I was to arbitrarily come up with a reaction and put in numbers there, I could easily say I had something like 3a plus 2b gives me c plus 4d. Okay, just arbitrarily. This is what we call a general chemical equation. The A's and the B's and the C's are just different chemical reagents and different products. But to pick up this concept, what we're looking at is, let's look at these numbers out in front. These numbers are what was used to balance the chemical equation. Okay, what about C? It doesn't have a number in front of it. That's because it's understood that it is a 1. Okay, so the concept of using stoichiometrics with chemical reactions is we are going to use these particular numbers and relate them to one another in what we call the mole ratio. Okay, the mole ratio is the ratio of moles between each of the products and or reactants. So for example, if I was coming up with a mole ratio for this particular chemical equation, I would say I have 3 moles of A to 1 mole of C. How did I get that? I have a 3 out in front of the A. I have a 1 out in front of the C. I have 3 moles of A to 4 moles of D. Where did I get those? Simply looking at the coefficients out in front of my chemical equation. I have 2 moles of B to 1 mole of C, and I have 2 moles of B to 4 moles of D. I can use any combination. These are just 4 of them. Okay. How many different ones are there? There's a total of 8 different mole ratios which I could find from this particular reaction. I just went from reactants to products, but I can also go from reactants to reactants. Okay, so I could actually write, I have 3 moles of A to 2 moles of B. I have 2 moles of B to 3 moles of A. Or likewise, I would have 1 mole of C to 4 moles of D, or 4 moles of D to 1 mole of C. So this is the big concept in this particular chapter. Okay, we are looking at the coefficients out in front and how we relate them to one another. So the topic of discussion for today, we are going to be talking a lot about this mole ratio. Okay, and with a mole ratio, you must have a chemical reaction. So you must be given some sort of chemical reaction that has these coefficients in it so that you can relate them to one another. I refer to that to my students as a chemical solution map. We must have these chemical equations in order to be able to solve these particular problems. Let's talk about these conversions. Okay, moles to moles. Now I kind of color-coded this, trying to help you out a little bit. We're talking about moles of a reactant to moles of a product. Okay, the only way we can go from moles of a reactant to moles of a product is we must have a chemical reaction. In other words, some sort of chemical equation must be given in order to convert from moles of a reactant to moles of a product. So when I'm going from moles of a reactant to moles of a product, I am going to use my chemical equation. What principle are we going to use? We are going to use the concept of mole ratio. Okay, so if the problem statement, and we're going to get to some problems here, some examples. If the problem statement asks you to convert from moles of oxygen gas to moles of H2O, they have to give you a chemical reaction. The chemical reaction will give you a solution map for how to solve that. In other words, we will look at the ratios out in front to determine how to go from this particular reagent to that particular product. Now, the easiest ones are the moles to the moles. We are now going to have to also be able to convert from grams to grams. And why is that? In the chemistry lab, we cannot just measure out moles. Okay, there's no such thing as a mole balance, so to speak. We have a balance that measures grams. So what I have to do is I have to measure out so many grams of this reagent, so many grams of that reagent, and mix them together. Okay? The thing is we've learned about these, right? And chemistry builds on itself. So we have to go from grams of a reactant to moles of a reactant. So I'm going to go from grams of my reactant to my moles of my reactant. How do we go from grams to moles? We use the formula weight of that reactant. Okay, if that reactant's oxygen, I got to use the formula weight of it. If that reactant is ammonia gas, we're going to use that. We have to use the formula weight to go from grams to moles. Now, if I'm going from moles of my reactant to moles of my product, okay, we just talked about this. Moles of a reactant to moles of a product. I must use a chemical reaction. Okay, so the problem statement must have some sort of chemical reaction in it. With that chemical reaction, I get a solution map from which I then use the mole ratios. Okay, so I'll use the mole ratios to go from moles of a reactant to moles of a product. So the first step is we'll use the formula weight of the reactant to go from grams to moles. Then we look at our chemical equation to go from moles of the reagent to moles of the product. And then the last step, I'm going to go from moles of a product. Excuse me, I have a typo here. This is to grams of a product. Grams of a product. Okay, so I'm going from moles back to grams. In order to be able to do that particular calculation, I'm going to have to use the formula weight of my product. When you're doing these equations, folks, they're going to be 3 steps, a lot of them. Okay, early on, when I show you a couple examples, they're only going to be 2 steps. But a lot of the equations, that you will be doing for my class will follow this particular model, grams to grams. Formula weight of the reactant, use the mole ratios, use the formula weight of the product, okay, to discover our answers that they're asking. And I'll show you what to look for as we go through this. Now, as you advance in your career and you do more chemistry, a lot of you are moving on, going to take General Chemistry 1. If you take General Chemistry 1, they're going to ask you to go one step further. Okay? And so I just want to, you have the ability to be able to do this type of stuff right now. You can go from volume to volume. And when I say that, volume of a reactant to volume of a product. In other words, if I was to ask you how much of this particular gas is produced that comes out of, say, the engine of your car, we could actually do that problem as long as I was given the chemical equation. We know enough about this. Okay, so we're going to go from the volume of the reactant to the volume, or to the grams of my product. How do I go from mass to volume? I would use the density. Hey, remember we learned that way back in chapter 2? That density stuff? Density is equal to mass over volume. So when we're doing these problems, okay, they just get more complicated because they're going to ask you or give you more things. If they give you the density and I know the volume, I can solve for the mass. Okay, so with this problem, they'd have to give me a chemical equation, they'd have to give me the starting quantities, and they'd have to give me the density if they expected me to do this. Now, once we get to this point, it's just like the previous example. Now I'm going to go from grams of a reactant to moles of a reactant. Okay, so moles of a reactant. How do I go from grams of reactant to moles of a reactant? I use the formula weight of my reactant. Now, moles of a reactant to moles of a product. Okay, how do I go from moles of a reactant to moles of a product? I have to use my chemical reaction. And with that chemical reaction, I use the process or the concept known as the mole ratio. I use those coefficients out in front of my equations in order to go from one reagent to a product. So I'm going to use that mole ratio then. Now I must go from moles of a product, excuse me again here, I have a mistake, to grams of a product. Grams of a product. How do I go from moles back to grams? Moles to grams is just using the formula weight. So that's the formula weight of my product. The last step in the volume to volume is to go from grams back to a volume. How can we do that? I must know the density of my product. Okay, so with these problems, right, you know all the material. Okay, it's just what makes them hard is that you have to know where to put them in order to get the correct answer. So with a volume to volume, you would use the density, the formula weight of the reactant, use the mole ratio to go from a reactant to a product, and then you would go use the formula weight of the product and then the density of the product in order to be able to solve this. Okay? What I'd like to do is let's start off with a simple one. Okay? And we're going to talk about chemical reactions used as a solution map for mole ratios. I've broke this one into two parts, an A and a B. Okay, so let's just look through it and read the problem statement. If 2.4 moles of O2 were allowed to react with an excess amount of iron, determine the moles of iron 3 oxide produced. And my students tell me, what is that problem asking for? Okay, look at the number they give you. If 2.4 moles of O2 were allowed to react, that is the number we're going to start with. Now, they told us it reacts with an excess amount of iron. Okay, so that means that in this case, iron is not prohibiting the reaction from occurring. Okay. In this case, which we will talk about, the limiting reagent would be my O2. So, when we're doing this problem, we're going to start out with whatever's given in the problem statement. So I have 2.4 moles of O2. Now, what am I converting to? They want to know moles of O2 to moles of iron 3 oxide. Okay, well, let's look at my chemical equation. What is iron 3 oxide? That would be this guy right up here. And my moles of O2 would be this guy right here. So when I'm doing this particular problem, I'm asking you to convert from moles of O2 to moles of iron 3 oxide. We would set this up like a dimensional analysis problem. Okay, where I put moles of O2 in the bottom because I want to get rid of that, and I'm going to put moles of iron 3 oxide, which would be Fe2O3, in the top. Where do I get these numbers? Moles of O2. Moles of O2, I get that from the coefficient that is out in front of my O2. The coefficient out in front of my O2 is a 3. So there's 3 moles of O2 for every 2 moles of iron oxide. So where does the 2 go? The 2 goes at the top. So in this particular case, what I'm going to do is I'm going to take the 2.1 and I'm going to multiply it by the 2 and then divide it by the 3 on my calculator. In that case, I will get an answer of 1.6 moles of Fe2O3. In this case, we used the mole ratio between the reactant, O2, and the product, Fe2O3. And I came up with my answer as 1.6 moles of Fe2O3. Let's look at part B. Let's read this question. It says, if 3.4 moles of iron, 3.4 moles of iron, were to react with an excess amount of oxygen. Okay, so in this case, my excess amount is going to be my oxygen, meaning this one is not my limiting reagent. Determine the number of moles of iron 3 oxide. Iron 3 oxide. So again, this problem statement has a lot of verbiage in it. What we're looking at is starting with the number that's given in the problem statement. So we look at it, 3.4 moles of iron. So I'm going to write out my 3.4. So I get 3.4 moles of iron. And it's asking me to convert from moles of iron to moles of iron 3 oxide, Fe2O3. The reason I put the moles of iron in the bottom, dimensional analysis, I'm able to cancel those out. Okay, which one is my iron up here? Just iron by itself. So iron just by itself, I have a coefficient of a 4 in front of it. So where does the 4 go? The 4 goes down here, with the 4 being in the bottom. Okay. Then which one goes up in the top? That would be the moles of Fe2O3. Fe2O3 is a product, so that number is a 2. Where did I get that from? Right up here. Right? That coefficient. We're using this concept of the mole ratios to be able to solve these problems. So 3.4 moles times 2 divided by 4 will give me the answer of the number of moles of Fe2O3. So in this case, when I put that in my calculator, I'm going to get 1.7 moles of Fe2O3. So if I only had 2.4 moles of oxygen, I could only make 1.6 moles of iron oxide. If I had 3.4 moles of iron, I could only make 1.7 moles of iron oxide. As you've seen in the lecture, these particular terms are extremely important. Okay, so we went through how to solve using these mole ratios. But in the problem statements, they're going to start to ask you things like, which is the limiting reagent? What is the theoretical yield? Which is the actual yield? And what is the percent yield? Be able to get you through each one of these. Okay, what is the limiting reagent? The limiting reagent is the reagent that is completely consumed in a chemical reaction. Okay, so in order to have a chemical reaction, we have to have two reagents. One reagent will end up being used up, where the other one will still be present. So the limiting reagent is the reagent that gets used up in order for that chemical reaction. It's similarly to what we talked about in the lecture video, where if I go to the refrigerator to make a cake, okay, and I need 2 eggs to make my cake, but when I get to the refrigerator I only have 1, it's going to limit how much cake that I can make. It's the same way in the concept of a chemical reaction. A limiting reagent will limit us on how much of a product that I am able to make. The theoretical yield. The theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of the limiting reagent. Okay, kind of confusing, but a theoretical yield is dependent on a limiting reagent. So a limiting reagent determines the theoretical yield. So if I went to that refrigerator and there was only 1 egg in there, that's going to limit me on theoretically how much cake or cookies I can produce. So when we look at these, okay, and I know it's not going to make a lot of sense right at the moment, okay, but what I want you to write down is when you're looking at the theoretical yield, when you're doing a math equation, you will end up determining the theoretical yield. It will be on the right-hand side of the math problem. Okay, so it'll be on the right-hand side of when we're doing these math problems. The limiting reagent, we usually start with reagents, so the reagent will be on the left-hand side of the problem. Okay, and this concept, left and right and so forth, right? There's no standard rule for it. But what I want to show you is if you set it up like I do, you're going to be able to find out which is the theoretical yield and which one is the limiting reagent. The theoretical yield will be on the right-hand side. The limiting reagent will be on the left-hand side. Let's talk about actual yield. The actual yield is the amount of product that is actually produced by a chemical reaction. Okay? So in the laboratory, when we do these chemical reactions, we mix them together, we are only going to get a certain amount. Why is that? Glassware may be dirty, right? You may have poor laboratory techniques. Okay, I don't like to pick on anybody, but a lot of my students, they like to get in and out real quick, so they'll do it as quick as they can, and they end up, not getting their glassware clean or not rinsing it all out. And so we get an actual yield from that reaction that isn't close to the theoretical yield. So the actual yield must come from a chemical reaction. You have to do the reaction in order to get an actual yield. Percent yield. The percent yield is the actual yield divided by the theoretical multiplied by 100. Now what that means is that, so to speak, what is the percent yield you expect to get from this particular reaction? And I tell students, think about it as though it's like your test score. What is the percentage that you would like to get? Right? If you get an A, get a 90%, that means you have a 90% in the class. Likewise, similar to a chemical reaction, a percent yield would be I had 90% yield for my chemical reaction. Now, remember, when we're talking about a chemical reaction, we're not looking at, so to speak, that arrow that comes in the generic chemical equation. A plus B goes to C plus D. Right? That A plus B goes to C plus D. But that arrow is the process. Okay, and I was a chemical engineer, and as a chemical engineer, we determine those processes to make those chemical reactions go forward. So those arrows, so to speak, that process, there's a lot to be expected in it. And the biggest one I can point out is in the pharmaceutical industry. Some pharmaceutical drugs cost an awful lot of money. New cancer research drugs, things of that sort. And the reason they do is because the process hasn't been developed as well yet. And for, let's say, for an example, if a reaction to make a certain new pharmaceutical cancer drug, they only get a 20% yield, they're going to have a lot more money in that particular process than if they were to get, say, a 98% yield like they do on aspirin or Tylenol or so forth, something that has been perfected. Okay, so when we're looking at these chemical reactions, we're going to ask ourselves, what is the percent yield? Okay, and the percent yield, the higher the percent yield, the better or more refined that chemical reaction is, and the lower the percentage yield, the less it has been refined. Okay, so in this particular example, I'm going to ask you, determine what is the theoretical yield and the limiting reagent for this particular reaction. Now, we just got done going over those terms, and we said that the theoretical yield is determined based on the limiting reagent. We also said that when we're doing these calculations, we look at the right-hand side to see what my theoretical yield is, and we looked at my left-hand side to see what the limiting reagent was. Okay, so if 2.4 moles of O2 were allowed to react with 3.4 moles of iron, determine the theoretical yield and limiting reagent. Have we seen this problem before? Right? If you flip back through your notes, you'll see we did this exact same problem with the exact same numbers. Okay? But in this case, I'm going to ask you, what is the theoretical yield and what is the limiting reagent for this particular reaction? So what I tell my students first is look at your reagents. I have two reagents. I have iron and I have oxygen. So when I set up these problems, what I do is I will put little brackets out here to signify my iron and my oxygen. How does that help me out? Well, when I look at the numbers that was given to me, I have 2.4 moles of O2, and I have 3.4 moles of iron. How does that help me out? The 3.4 goes next to the iron, and the 2.4 goes next to the O2. Okay, so if you write your reactants, just put them in brackets on the left-hand side. It'll help you set up your problem. So I'm going to start with the 2.4 or the 3.4 moles, whatever one. I have 2.4 moles of O2 and 3.4 moles of iron. They're asking me to determine the theoretical yield and limiting reagent. The theoretical yield and limiting reagent of what? Of the product. Okay, of the product. In a generic chemical equation, I would have A plus B goes to C plus D. Normally, I am given two products. Okay, and so then they'd have to ask me, determine the theoretical yield and limiting reagent for product C or product D. Well, what is it in our case? In our case, I only have one product. So since I only have one product, right, they kind of get away with asking what is the theoretical yield and limiting reagent without putting a unit behind it, because there's only one product in this particular reaction. So what that means is I'm going from moles of iron to moles of iron oxide. And I know we did this problem before. I'm going from moles of iron to moles of iron oxide. And in this one, I'm going to go from moles of O2 to moles of my iron 3 oxide. Where did we get those numbers, right? We have to look at the coefficients. What are the numbers out in front of everything? I have a 4 in front of the iron. I have a 3 in front of the oxygen and a 2 in front of the iron 3 oxide. So by the iron, I get a 4. The Fe2O3 gets a 2. By the O2, I have a 3, right? Because that's the coefficient out in front of my chemical reaction. And then out in front of the Fe2O3, I have a 2. So in my calculator, I'm going to put 3.4 times 2 divided by 4. 3.4 times 2 divided by 4. I get 1.7. So I get change my color here, 1.7 moles of Fe2O3, right? Because the moles of iron cancel out. And then in the next one, I'm going to put 2.4 times 2 and divide by 3. And I get 1.6 moles of Fe2O3. Now again, the moles of the O2, they cancel out. In this problem statement, we did all this mathematics because they want to know which one is the theoretical yield and which one is the limiting reagent. Okay, and as we talked about in the previous slide, I said the theoretical yield, when you're doing your math problem, you will find it on the right-hand side of the equation. Meaning, over here is going to be my theoretical yield. What determines my theoretical yield is my limiting reagent. Which I said you will find on the left-hand side when you're doing these problems. Okay, so it's going to help if you set them up this particular way. All right, so which one is my theoretical yield? 1.7 moles of Fe2O3 or 1.6 moles of Fe2O3? My theoretical yield is the maximum amount of product that can be produced based on the limiting reagent. So, back to that analogy of baking. If it takes 2 eggs to make a dozen cookies, and I go to my refrigerator and I only have 1 egg, I can only make 6 cookies, right? So, when we're looking at this, we're always going to pick the smaller number of the two, 1.7 or 1.6. In our case here, 1.6 moles of Fe2O3 is the smaller of the two. So that becomes my theoretical yield. My theoretical yield is determined based upon my limiting reagent. So if I draw my arrow back, in this case, my limiting reagent becomes O2. So to answer this problem, what is the theoretical yield? It would be 1.6 moles of Fe2O3. What is my limiting reagent? It's going to be O2. Now, had I done this problem and this 1.6 was like a 1.9 instead, I would have picked the top one, 1.7. That would have been my theoretical yield. And then if I would have chose 1.7, then iron would have been my limiting reagent. Okay, so it helps to keep these in line. That way you can determine what your limiting reagent is based on your theoretical yield. Let's try this problem again, but with a different twist on it. We're going to start out with, what's the problem asking me? Okay, I have 2.4 grams of O2 and 3.4 grams of iron. Now, how is this problem different than the previous problem? The previous problem, we had just moles, but in this problem we have grams. So I'm going to have to do one more conversion. I'm going to have to go from grams to moles, use my mole ratio, then back to grams. Determine the theoretical yield in grams and limiting reagent. Okay, so let's get started with this one. What do I do? On the left-hand side, I always start out with my brackets, right, so to speak. I'm going to put my iron over here, and I'm going to put my oxygen over here. This just helps me keep things in line. Next to the iron, how many grams of iron do I have? I have 3.4 grams of iron, and I have 2.4 grams of oxygen. Now, what did we say? The first step is to go from grams to moles. Then I'll go from moles to moles, and moles back to grams. So to go from grams to moles, I'm going to use the formula weight of my reactant. And to go from moles back to grams, I'm going to use the formula weight of my product. And then the new concept, to go from moles to moles, I use the mole ratio. Okay, so this is going to be our solution map for determining these particular problems. So let's start at the first one with iron. I'm going to go from grams of iron to moles of iron. Okay, what's our definition? 1 mole of anything is equal to its atomic mass in grams. So 1 mole of iron from the periodic table is equal to 55.85 grams. My next step, then, since moles of iron is in the top, I'm going to put moles of iron in the bottom. Dimensional analysis. Why? Because I want them to cancel out. Now, it's asking for the theoretical yield. How many products do I have in this reaction? I only have one product. So that's going to be the one I'm going to be looking at. So this is going to be moles of Fe2O3. Now, what is the number out in front of the iron? That is a 4. What is the number out in front of the Fe2O3? That is a 2. So the 2 goes on the top and the 4 on the bottom. Now, it asked for theoretical yield in grams. Okay, so I can't stop here. I have to go back and use my formula weight of the product to do one more step. So, since I left off with moles of Fe2O3 in the top, I'm going to put that in the bottom so they cancel out. And grams of Fe2O3 go in the top. Now, we've already used this mole ratio. This is the number one mistake I see on students' papers. Okay, when we're talking about the formula weight is a definition. 1 mole of anything is equal to its atomic mass in grams. Okay, so notice how I have grams in the top, moles in the bottom. Students are like, well, I want to put that 2 that's on the chemical reaction there. No, we already took care of that. So by definition, 1 mole of anything is equal to its atomic mass in grams. So the 1 always goes next to the mole. 1 mole of Fe2O3 is equal to how many grams? Well, in this case, we're going to have to determine what the formula weight is of my Fe2O3. That's going to be 2 atoms of iron at 55.85 plus 3 atoms of oxygen at 16. So 2 times 55.85 plus 3 times 16 is 159.7. So I have 159.7 grams of Fe2O3 is equal to 1 mole. So the 159.7 goes up here. Okay, so now I got this big long conversion, dimensional analysis. I multiply through whatever's in the top and divide by what's in the bottom. So on my calculator, I would put in the 3.4 times 1 divided by 55.85 times 2 divided by 4 times 159.7 divide by 1. And on my calculator, I get 4.86105. And that is what? That is my grams, apologize, I'm running out of room here, of Fe2O3. Now we must do the next reagent. In this case, it's going to be oxygen. Okay, so I have grams of O2 to moles of O2. Well, if it's the formula weight of the reactant, this time I'm not just talking about oxygen, I'm talking about O2. I'm talking about the diatomic version. So I got to take 2 times 16 to give me the 32 grams. So there's 32 grams of oxygen in 1 mole of O2. Moles of O2 go in the bottom, and moles of Fe2O3 go in the top. Put the moles of O2 in the bottom because I want them to cancel out. Now, I'm going to go up and I'm going to look at my mole ratio. There's a 3 in front of the O2 and a 2 in front of the Fe2O3. So I put a 2 here and a 3 here. This is my mole ratio. I'm going from moles of a reactant to moles of a product. I'm not done yet because I have to convert to grams of Fe2O3 from moles of Fe2O3. How do I know the moles of Fe2O3 go in the bottom? Because I need that dimensional analysis. I need it to cancel out as I go across. Okay, we look at this. Which one gets the 1? Right? 1 mole of anything is always equal to its atomic mass in grams. So the 1 always goes next to the mole. What did I get for the atomic mass of Fe2O3? 159.7. So in my calculator, for this equation, I'm going to do the same thing. Now, we all know the identity property. If I multiply by 1 or divide by 1, I'm going to get the same answer. Okay. So, but if it helps, put it in your calculator. I just kind of go up and down as we go back and forth across. So I'm going to put in 2.4 times 1 divided by 32 times 2 divided by 3 times 159.7. Okay, and you can divide by 1, you'll get the same answer. And I get 7.985. Okay. Some students like to multiply across on the top, multiply across on the bottom, and then divide them at the end. You can do that as well, right? If you have a scientific calculator, it knows the order of operations, so you can just go multiply, divide, and it gives you the correct answer when you get to the other end. Now, it's asking for what is the theoretical yield and the limiting reagent. Okay, the theoretical yield is the maximum amount of product that can be generated based on the limiting reagent. So when I look at the right-hand side of my equation, I'm going to look for the smaller number of the two. Okay, in this case, it is the 4.86105. That is going to be my theoretical yield. So my theoretical yield is going to be the 4.86105. Now, when you're putting this in for your homework, remember, we have to remember significant figures. So I try to make this as simple as possible. Whatever you start with is what you must end with. 2.4 has two significant figures. 3.4 has two significant figures. So in your answer, you must put this in your homework. Your answer would be two significant figures. So I have a 4 and I have an 8. I look over at the next number. That is a 6. So what does that do? That bumps that up to 4.9. So my theoretical yield is 4.9 grams of Fe2O3. Now, my theoretical yield determines what my limiting reagent is. So I draw my arrow back, right? Had I chose the one on the bottom, I would have drawn the arrow back to the O2. But since I picked the 4.9, my correct answer for my limiting reagent then is the iron. Okay, so my iron is now my limiting reagent. So it seems like a lot of work, right? There's a lot of steps involved in solving these problems. But in order to properly determine the theoretical yield and the limiting reagent, you have to look at both reactants, okay, to see which one is. You look for the theoretical yields, you pick the smaller of the two theoretical yields, and then you draw your arrow back, and that will tell you what your limiting reagent is. Let's look at another example, okay, and we're going to introduce this concept of percent yield. So determine the theoretical yield, the limiting reagent, and the percent yield for this particular reaction. Okay, so if 114.5 grams of copper 2 oxide, 14.5, were to react with 11.5 grams of carbon and 87.5 grams of carbon are obtained. Excuse me, that's not supposed to be carbon, it's supposed to be copper. So please make the note. Are obtained. Determine the theoretical yield in grams, the limiting reagent, and the percent yield. Okay, so in this particular reaction, how many numbers are they giving me? They are giving me 3 numbers. I have the 114.5 grams, 11.5 grams of carbon, and the 87.5 grams of copper. I do apologize about that mistake. So we're going to treat this just like we did all the other problems we did. What I want you to start out with, what are the reactants? I have, this is a reactant, this is a reactant. So I'm going to have Cu2O, and I'm going to have carbon. So let's put the numbers appropriately by them. 114.5 grams of Cu2O and 11.5 grams of carbon. That takes care of two of the numbers. The third number is 87.5 grams of copper was produced. Now, look at the units on this. Grams of copper. Cu. Where do we see U? Cu is on the left side, or excuse me, the right side of the chemical equation. Since that copper is on the right-hand side of the equation, that becomes a product. So this is a product. Specifically, the number they gave me is going to be my actual yield. Okay, so when I read this problem statement, if 114.5 grams of copper oxide were to react with 11.5 grams of carbon, 87.5 grams of copper are obtained. Determine the theoretical yield in grams, the limiting reagent, and percent yield. So notice, just look at the units beside. I tell my students that copper is the only one that is on the right-hand side that we're interested in. Okay, so what does that mean? This problem statement's not asking anything about the carbon monoxide. So we can just put an X through that. We're not going to be looking at determining or finding the theoretical and or actual yield for those particular ones. Okay, so then this becomes a problem just like we did before. I'm going to go from grams of copper 2 oxide to grams of what? Grams of copper. Okay, because we've picked the product by looking at the problem statement. All right, so the first step is to go from grams of Cu2O to moles of Cu2O. Now, how do we go from grams to moles? We use our formula weight. Okay, so I would have to find out what is the formula weight of Cu2O. That's 2 coppers and 1 oxygen. My formula weight for Cu2O is 143.10 grams per mole. Okay, so I'm going to put 1 mole of Cu2O is equal to 143.10 grams of Cu2O. My next step is to go from moles of Cu2O to moles of what? Moles of copper. Why? Because that is my product that I'm looking to go to. And the reason I put the Cu2O in the bottom is because I want that to cancel out. Well, now I'm going to use the new process. I'm going to look at the mole ratio. What is the coefficient out in front of the Cu2O? That is a 1. What is the coefficient out in front of the Cu? That is a 2. So I'm going to put a 2 out in front of here. Now, I'm not done because I need to go back to grams. So I'm going to go from moles of copper back to grams of copper. Again, I want those coppers to cancel out. So by definition, 1 mole of anything is equal to its atomic mass in grams. So 1 mole of copper is equal to, what's the weight of copper on the periodic table? 63.55. Okay, so now I have to solve for this. In my calculator, okay, I'm going to negate the ones, but I'm just going to go up and down like we did before. So I'm going to put in 114.5 divided by 143.10 times 2 times 63.55. Okay, and on my calculator, I get 101.6977. Now, I started with four significant figures up here. I have 3 significant figures here and 3 significant figures in my actual yield. Okay, so in this case, when we're doing this problem, we want to keep them with the least significance. So let's do 3 significant figures. Okay, so let's do 3 significant figures with this. So I'm going to count over. I've got 1, 2, 3. Look over for the next one. So in this case, my answer would be 102 grams of copper. Now we've got to do our other reagent, the carbon. I go from grams of carbon to moles of carbon. 1 mole of anything is equal to its atomic mass in grams. So in this case, it's going to be 12.01. That's the mass of carbon on the periodic table. I then go from moles of carbon to moles of copper. Again, why am I going to moles of copper? Because that's what my actual yield was given in, right? We're not worried about that carbon monoxide. Had the problem statement asked me to do carbon monoxide, then I would be concerned with it. All right, so now we're going to use that mole ratio in front of it. What's the number out in front of the carbon? There's no number there, so that is a 1. The number out in front of the Cu is a 2, so I'm going to put a 2 there. Again, my last step is to go from moles of copper to grams of copper, because they asked me to determine that. 1 mole of copper is equal to 63.55 grams of copper. And where do I get that? That's the formula weight off the periodic table. So, in order to solve this one, I'm going to take the 11.5, multiply it by 1, divide by the 12.01, times 2, times 63.55. Okay, and when I do that, I end up with 122 grams, or excuse me, 121, getting ahead of myself, 0.702 grams of copper. Again, we said we were looking for 3 significant figures, so this would be 122 grams of copper. All right, so I have 2 numbers, and what I'd like to call out your attention is that in both numbers, they both have the same units, okay? If you do not have the same units, okay, then you're probably going to get the problem wrong. You want your units to be the same. We are calculating the theoretical yield in grams. Okay, so grams of what? The only one we're concerned with is the copper. So grams of Cu. Now, I'm going to determine what is my theoretical yield. My theoretical yield I determine from my limiting reagent. Right? So in other words, I'm looking for what number is smaller of the two. In this case, the 102 is smaller than the 122. So the 102 becomes my theoretical yield. So my theoretical yield is 102. Okay, so I have a theoretical yield of 102. Since I picked the top one, I must draw my arrow back, and then that gives me my limiting reagent. Okay, so my theoretical yield is 102 grams of copper, but my limiting reagent was copper oxide. Okay, so I draw that arrow back. That gives me my limiting reagent. It also asked for one more thing. It said, what is my percent yield? Okay, my percent yield is my actual yield divided by my theoretical multiplied by 100. Where did I get my actual yield? Well, we said that that third number was my actual yield. So that'll be my actual yield. My theoretical yield is what I determined when I did the first process. Okay? So I'm going to take the 87.5. I'm going to divide it by the 102. I'll put these units in here for you to notice how they cancel out. Grams of copper, times 100. So 87.5 divided by 102 times 100 gives me 85.78% yield. Now again, we're keeping with the concept of three significant figures. So I look over here. The correct answer I would report on my homework is 85.8%. Okay, so with these problems, there's several steps involved. Several steps. You got to go from one to the next and so forth. But what you'll find, and what I find most of my students do, is they actually enjoy these problems, right? Because they're kind of systematic. Once you determine what the chemical reaction is, okay, you'd take the starting reagents, you use the mole, or you use the formula weight, the mole ratio, and the formula weight. That will help you to determine what your theoretical yield is. Once you determine your theoretical yield, you can find your limiting reagent, and then take that theoretical yield to find your actual yield. So we just got done doing a problem. We're going to do a problem exactly the same way. The only thing different is it's going to be a new problem, and the wording is going to change a little bit. Okay, so I don't want you to get tripped up over the wording, so I just worded it a different way, so that way to help you out. So determine the theoretical yield and limiting reagent and percent yield for this particular problem. A chemist allows a reaction to occur with 185 grams of my iron oxide and 95 grams of CO. Okay, so I'm looking at my iron oxide, my CO. He collects 87.4 grams of what? Of iron. So if he collects 87.4 grams of iron, then iron is going to be the only product that I'm going to be concerned with. So that means I'm not going to be worried about the CO in this particular case. And so let's look at this particular reaction. I need to go from grams to moles. So it might be a good thing to start out with, determine the ones you're going to use, and then find the formula weights for each of the ones that you need. So if I need the formula weight of Fe2O3, and I think we solved that one in our earlier one, we got 159.7 grams per mole. And we need the formula weight of carbon monoxide, and that is 12.01 plus 16, so that gives me 28.01 grams per mole. And I will need the formula weight of iron. In this case, that's going to be 55.85 grams per mole, and I get that off the periodic table. Now, the reason we need the formula weights again is because I am going from grams, right? I'm starting with these grams. If I was to start with moles back in that earlier problems, I would not need the formula weight. Okay, so just like before, let's draw our little brackets here. I'll put Fe2O3 in the top one, and I will put CO in the bottom one. Now, does it matter which one you do first? It does not matter, right? You could do the carbon monoxide first if you would like to. The 185 grams of Fe2O3 go in the top, and the 95.3 grams of CO go in the bottom. I am given a third number, 87.4 grams of iron. What is this number? This number is going to be my actual yield, right? They're going to give me my actual yield. He collects 87.4 grams. That means he did the reaction, and this is how much he collected, right? It's our job to determine what that theoretical yield is. So I'm going to go from grams of Fe2O3 to moles of Fe2O3. 1 mole of Fe2O3 is equal to how many grams? 159.7. How do we determine that? That was my formula weight, right? Grams of Fe2O3 cancel out. I'm left with moles. Moles of Fe2O3 to moles of Fe. Where do I get these numbers? Right? These are the mole ratios. So I have 2 moles of Fe to 1 mole of Fe2O3. My last step is to go from moles of Fe to grams of Fe. So 1 mole of anything is equal to its atomic mass in grams, 55.85 grams. So in my calculator, I'm going to put the 185 and divide that by 159.7, multiply it by 2, and then multiply it by 55.85. And I'm getting a number of 129.395. 129.395. That's grams of iron. Now, when we do this, we'll have to remember I only am as accurate as 3 significant figures. So my answer is going to be 129 just 129 grams of iron. Let's do the other reagent. So I got carbon monoxide. So I'm going to go from grams of CO to moles of CO. 1 mole of anything is equal to its atomic mass in grams. So the formula weight of CO we determined was 28.01. I'm then going to go from moles of CO to moles of iron. Again, why am I going to iron? Well, the problem statement or the actual yield was given in grams of iron, so that's why I've chosen that one. I then have to go up and look at the number in front of the CO is a 3. The number in front of the iron is a 2, so that's my mole ratio. For every 3 moles of carbon monoxide, I can generate 2 moles of iron. My last step is to go from moles of iron back to grams of iron. 1 mole of anything is equal to its atomic mass in grams, so I look up the weight of iron. Iron is 55.85 grams. So on my calculator, I'm going to do the 95.3 divided by the 28.01 times 2 divided by 3 times 55.85. And I got an answer of 126.68 grams of iron. Okay, and again, 3 significant figures. Look over, this is going to make this 127 grams of iron. Okay, so which one is higher, 129 or 127? Right? In our case, it's going to be, or excuse me, which one is lower? I always pick the smaller number of the two. So in our case, it is the 127. So this becomes my theoretical yield. My theoretical yield governs my limiting reagent. So in this case, carbon monoxide becomes my limiting reagent. So now I have to determine what is my actual yield. And my actual yield, or my percent yield is my actual, which was given, the 87.4 grams, divided by the 127 grams. So 87.4 divided by the 127 gives me 68.8%. So again, with this problem, we're just doing the same formula weight of the reactant, mole ratio, formula weight of the product. The only thing different is, and what you folks will come to find out as you advance on, whether it's beyond my class or so forth, the problem statements are what really trips up my students, right? Whether it says a chemist collects, whether it's a baker, what have you, okay? Don't get caught up in the erroneous information of the story problem. So I'd like to start off with our, or talk about our last type of problem that we were going to talk about today, and that is the stoichiometrics with heat of reaction. Okay, and when we have a chemical reaction, either heat is given off or heat is taken in. In other words, it either takes energy to make that reaction, or that reaction makes energy. Okay, and the thing that people think about chemistry is they're always thinking about the explosions, the loud bangs, the beautiful colors, so forth. Those are exothermic reactions. Those are reactions that give off energy. Okay, now there are some reactions which we can't get to occur unless we apply energy. Okay, so some reactions take energy, some reactions need energy. In our particular example here, we have propane, which is what you folks use in your gas grills and so forth, mixed with oxygen to give carbon dioxide plus H2O. And we've learned throughout the semester the different types of chemical reactions. This is a combustion reaction. Well, do we need heat for this to occur, or does this produce heat? Well, I hope you can answer this correctly, right? Because when we're using our gas grill, the reason we're using it is we want it to heat up our food, right? So we want it to give off heat. So it's going to give off energy. And the reason I try to bring this up to begin with is look at our heat of reaction for this particular reaction. Okay, notice how it is negative 2044 kilojoules. Okay, so that means that this reaction is giving off energy. Okay, and it's out of the scope of this particular class to talk about. If you take my general chemistry 1 or so forth, we get more advanced in that, but it has to go to deal with what is the surroundings, what is taking in the energy, and what is giving off the energy. Okay, and we have to define our systems and all that. And I didn't want to do that in this particular class. We're just looking at this particular reaction. We know it is a combustion reaction, and we know it gives off heat. If we have a small LP gas propane tanks that contains roughly 12 times 10 to the 3 grams of propane, to determine the heat in kilojoules for propane given a complete combustion occurred. Okay, now we're using stoichiometrics with this particular reaction. So what I want you to do is, what are the numbers out in front? That's the whole concept of this unit, these numbers out in front. What is the number out in front of the C3H8? Okay, so the C3H8 has a 1 out in front of it. So that means I only have 1 mole of propane to react with 5 moles of oxygen and so forth. So what I can do is my delta heat of reaction is equal to negative 2044 kilojoules per mole of propane, C3H8. Now this is specifically for my propane. If I was to look at the H2O or the CO2, right, I would have to use those with the appropriate moles. So in other words, I would take the 2044 kilojoules and divide it by the 3 moles of CO2 or the 4 moles of H2O. So those are specific for those particular types of problems. But in this case, since propane just has 1 out in front of it, I know that the heat of reaction given off is roughly 2044 kilojoules. So let's start with what's given in the problem statement. The 12.0 times 10 to the third grams of propane. Now I've got to go from grams of propane to moles of propane. And how do we do that? Well, to go from grams to moles, we know that's just the formula weight. 1 mole of anything is equal to its atomic mass in grams. So we have to find what is the formula weight of my propane. So I have 3 carbons at 12.01 plus 8 hydrogens at 1.01. So my formula weight for propane is 44.11 grams per mole. So I have 44.11 grams per mole. Now I know for 1 mole of C3H8, the reaction puts off 2044 kilojoules. So in this case, I will take the 12.0 exponential to the third, divide it by the 44.01, and then multiply it by the negative 2044. And I get 15.5
557.327.88. I have 3 significant digits, so my answer is going to be 5.57 times 10 to the 5th kilojoules. That is how much energy would be given off in a single propane tank that we use on our simple gas grills. Now, I'm not going to ask you to do these particular problems on the exam or so forth, but what I want you to take away from this is stoichiometrics, this concept of us balancing chemical reactions and be able to balance them. It opens up a lot of doors for us to be able to calculate how much energy is given off for, say, like a propane tank. It also helps us how much of a product can be produced, theoretical yield, limiting reagent, percent yield, and those types of things. So stoichiometrics really opens up our horizons in the chemistry field for being able to manipulate and find new quantities. Well, again, I thank you for your time. If you have any questions about any of this material, please don't hesitate to send me an email, okay? If you're having problems with a certain portion of it or so forth, the only thing I ask is, since these are getting really math intensive, is that you just shoot me an email, send me a picture of what you're working on, okay? It kind of helps me out a little bit, see where you're at, and then I can maybe say, oh, you divided wrong here, or you didn't do this right, or so forth, okay? If you have any questions, please don't hesitate to email me, and have a great day.